The next thing we're going to do is draw and label a spectrum. So I gave you propanol to work with, and I've drawn that out for you. First thing we're going to do is count signals. Easiest one to see immediately is this hydrogen by itself in the corner. It has to be its own signal. Next up, we have this carbon, which has 2 hydrogens on it. That is going to be our second signal. 1 carbon over, we have these 2 hydrogens. They are their own separate signal. And last but not least, these 3 hydrogens will be their own signal. I have gone ahead and color-coded these based on what we talked about. Next, we are going to look for the integration. Even though that was number 4, we're going to do that first. So, starting from left to right, the red hydrogens, there are 3 of them, so we're going to go ahead and write 3H. For the green hydrogens, there are 2, so we'll go ahead and write 2H. For the blue hydrogens, again, we have 2H, and for the purple, we are going to have 1H. This is very, very straightforward, but it can be a little bit weird looking on the actual spectrum, so that's why I mention it now. Before we go on to actually drawing the spectrum and putting these together, I do want to go over what's happening in the spectrum. So here, this axis is ppm, and it's usually from 0 to 12 for hydrogen NMR, but I am going to just put 5 for these purposes. And we're going to go over the general layout. So pointing towards the left, or the higher number, we're going to say that that is downfield. And we have D and D, de-shielded. The opposite way is the complete opposite. It is upfield, and it is shielded. Something that is also used in textbooks and such, Dr. West doesn't tend to use it, is frequency. Downfield would be high frequency, and upfield would be low frequency. And I don't have space, so I'm going to shorten it. All right, so what does this mean, right? I'm going to give you a little analogy. It's not exactly how things work, but it's an easier way to think about things. So let's say we have 2 nuclei, right? One of them has a huge electron density around it, a lot of protection. The other one has very little electron density around it, very little protection. The one that has the most density, we're going to kind of use the words density and shield synonymously. So the electron density is the shield that's protecting this molecule. And the electron density, the shield, is going to protect it from these beams that are going to hit it, like in the NMR machine. So if we hit this thing with 4 beams, only one of them are going to go in because this shield is so efficient. But over here, if we shoot 4 beams again, this is so inefficient that most of the beams are going to go in. And so if you think about it, the bigger your shield, the fewer things can penetrate the shield, so you have a smaller number. That's why more shielded is a smaller number on the spectrum, versus the smaller shield, aka more de-shielded, has more rays hitting it on the inside, so it's higher because there are a higher number of rays hitting that nucleus.
Now I'm going to go ahead and erase this, and we're going to actually do the spectrum. First one we're going to graph is going to be the purple hydrogen. And the reason for that is since it is attached to an oxygen, which is an electronegative atom, it is going to be the most de-shielded because its electron density is going to be pulled away from it, right? And we're going to do chemical shift and multiplicity together pretty much. So as we can see, this oxygen is between the hydrogen and any other possible neighbors. So we know that we are going to use the n+1 rule when finding the multiplicity. So I'm going to go ahead and put that here for you. And as I said, we're going to start with the purple one. So I actually realized they were color-coded incorrectly, so I went ahead and fixed that for you guys. So starting with the purple one, we know that it has 0 neighbors. It can't have any because of the heteroatom in the way. So 0 plus 1 gives us a singlet. And a singlet will look like just one little peak by itself. And 1H is the integration, so we are going to write that on top. But another way we can talk about integration, or rather show integration, is a little squiggly line like this. It'll make more sense once I do all the other ones. Next up, we have the blue hydrogens. The blue hydrogens have 1 bond length, 2 bond lengths, and 3 bond lengths. So they have 2 neighbors, the neighbors that are the green hydrogens. 2 plus 1 is 3, which is going to be a triplet. The triplet looks like so. 1, 2, 3. And the reason that it is going to be closest to the higher number is because it is closest to the heteroatom. Now, when we're looking at the green hydrogens, we already saw that it has 2 blue neighbors, so I will go ahead and write that in. But we also have to look at the other side since it is in the middle. 1, 2, 3. Wow, so all of these red hydrogens also count as neighbors, so we're going to do plus 3. 2 plus 3 plus 1 will give us 6 as written here, and that is going to be a sextet. For now, we're going to call it a sextet because I want to give you guys the official name. However, in general, anything above 5 is just going to be called a multiplet, just for simplicity's sake. And the sextet is going to look kind of complicated, but all you have to remember is that you're going to have an even number of peaks on each side, aka at each height. So it will look like this, right? And oh, my bad, I forgot to put 2H right here. And again, we're going to have 2H for the green signal. I am so sorry for my dog barking in the background. But now I'm going to show you why the squiggly lines are important. So the squiggly line that I drew here is essentially like a ratio. And it's showing us the relationship between each of the peaks. So since the blue signal is 2 times as many hydrogens, this squiggle is going to be approximately 2 times as tall. Same for the green. Last, but certainly not least, is this red signal. And we already said that the red signal has these 2 green hydrogens as neighbors. So we're going to go ahead and do 2 plus 1 is 3. We have another triplet. So I will draw that in. And that is going to be closest to 0 because it is furthest away from the heteroatom. So it has a better shield of electrons around it. Last but not least, this is 3H for the integration. And that means this little squiggle is going to be approximately 3 times the height of 1H.